Okay, so now we're going to talk about something called Mohrs Circle. And so if you remember stress elements, if you wanted to find out what the principal stresses were, or the maximum in-plane shear stresses, or how to find the stresses along a different orientation, you had to go find the equations and you had to plug them in, and you would get the results. Now, I want to talk to you a little bit about how we find those things. So those equations make a little more sense for one, and then there's another way that some of you may find easier, and some of you may find that the equation is a little easier. It just depends on preference. But this will at least show you a little bit more about how those equations came to be, as well as another way that you can find these things out. And it's called Mohrs Circle. And so if you have this stress element, if you rotate it, you'll have there's a circle of stresses that will be applied, and it'll just rotate around that circle. And I'll show you how that works. And so if you draw a graph, and we're going to have this axis will be your normal stress axis, and for reasons that I don't fully understand, this will be your shear stress axis, and your positive will be going down. That's just the way it is. I'm not sure why. All right, so let's find our points. We know that our normal stresses are being applied at 5 psi, and so let's draw our stuff. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so this is our axis, and so we have one normal stress being applied right there on our normal stress axis, 5 psi, and we have another here at 10 psi. And we know that there's also being a shear stress being applied at 3 psi, so that'll be right about here. And so what we want to do is we want to find out now what the circle is going to look like. Okay, so we're going to find, the x component, the x one we know is 10, so this is the sigma x, and this one, that's too small, you can't see that. All right, so this one is sigma x, and this one is sigma y. And we're going to take our shear, and in this case it's positive, in case I never told you that. Positive is when it's going up into the right corner, and negative is when it's going down into the right bottom corner. And we're going to take that shear, which is 3 psi, and we're going to apply it here to the x component. So we're going to put it right there. And then we're going to draw the negative version of that, so the negative 3, 1, 2, 3, right there. I'm going to draw it on the y component. And so you have 2 points. You have the xy, the normal shear point right there, and then the normal shear point right there. Remember that the positive one, or if it's positive, the positive goes there on the stress x. If it's negative, it will be up here, and so it'll just be the opposite. But the positive and negative orientation for the shear stress is, I don't know. Anyways, so what we do now is we can draw, we'll say triangles between those 2 points, or a line between the 2 points right there. And now we draw a circle around it. That is our diameter. And so we have, in that case, a circle that runs right around there. And so these 2 points, those tell us what our stresses are. And if we were to rotate it, we would rotate it so much, we'd have a point like right here, or right here, or right here. And so if we had our points right here, say, we were to rotate it so much so it's oriented like that, then our normal stresses would be like, I don't know, 8.5 and 5.5, 6.5 or something like that. And our shear stress would be more like 4 or something, or no, it would be less than 4, but 3.2 or something. So that circle is what we'll use now to find out what our principal stresses and our in-plane shear stresses. Now our principal stresses are where our maximum normal stress is. Now I want you to look at that circle, and I want you to think about where that's going to be. Where would that maximum normal stress be? Where on that circle is the biggest value of the normal stress. And well, yeah, it's right here at the farthest over, and its companion would be right here on the other side. And so those will be our principal stresses, and that's where the shear stress, you can see, is going to be right here at 0. And so let's, how would we go about doing that? First, let's find out where the center is. So I want to find out where the center of this circle is. And so our center, we can find it just by using our head, but we know that the center is going to be the average of these 2 points, 10 and 5. So the center is equal to sigma x plus sigma y over 2, our average, so 7.5. Well, if you just look at that, you could actually probably figure that just by looking at that. And so we know that is 7.5. Okay, I also want to know what my radius is, a radius of the circle, and we can actually do that by looking at this triangle. We have a triangle right there. We know what this, well, we want to know what this is. That's our radius. That's what we want to know. We know what this height is because it's 3, right? It's the height of our shear. And I want to know what this length is right there. I want to know what that length right there is. And to do that, I really just take our center and we subtract the lower point, which is 5, and we find out that this length is 2.5. All right, so let's use Pythagorean's theorem. We plug this into Pythagorean's theorem, so our r will be equal to the square root of 2.5 squared plus 3 squared. It's Pythagorean's theorem, and we find out that the radius is 3.9. 3.9051. Okay, we know the radius now. And so now we can find our principal stresses by taking that center point and adding 3.9051 to it, or subtracting that radius from it. And that'll put us right there and right there. And so we find out that our principal stresses, sigma 1 and 2, we'll call it, is equal to 11.4, and so that's that point, 11.4, and 3.5, or 3.6, I guess. 11.4 and 3.6. Okay, that makes sense, right? It's pretty simple. Now I want to find out what the maximum shear is. Now I want you to look at that circle again, and where do you think the maximum shear is going to take place? Now remember that this is the shear axis, and so what is the highest and the lowest that this shear can possibly get? And well, it's going to be the top of the circle, right? The top and the bottom. So the opposite side. And so that, well, that's easy. That's just the radius. The radius up and the radius down. And so then we know that our maximum shear for this element is going to be equal to 3.9051. Now, you can find the angle at which this is going to occur. So we want to find out how much you have to rotate it to find those principal stresses. Now that's where people tend to get tricked up just a little bit. I want you to look at this element first, and I want you to think, how much do you have to rotate this square until it looks exactly the same again? And the answer is, well, you can rotate it 45 degrees, right? And then this side is over here and this side is over there. And so you rotate it 45 degrees and then you get the square again. Now if this, how much do you have to rotate the circle in order for it to look the same again? You take this spot and you rotate it. You have to rotate it. Oh, sorry, I made a mistake. You rotate this 90 degrees and that'll get you to the exact same spot. You'll have to forgive me, but yeah, that's 90 degrees, and so you have to rotate this 180 degrees. And so whatever angle you find here, you rotate the stress element half of that in order to get these stresses. And so I want to find out what this angle here is, and we'll call it phi. How much you have to rotate it to get the stress points? Well, that's pretty simple too. I'm going to take the tangent of the opposite over the adjacent. So tangent of 3 over 2.5, and that'll give me, I think, 50.2. Now I know that in order to rotate the stress element, that's going to be half of that. And so that'll be 25.1. So we'd rotate this piece 25.1 degrees to find our principal stresses. Now we do the same type of thing with finding the shear stress. We just rotated the other direction, and we're going to call this angle, I don't know, alpha. And we do it the same way. The opposite over the adjacent, take the tangent of it and divide it by 2, and that'll give us alpha, which we find to be, oh well, I guess that one's alpha, and so this, whatever, alpha is equal to 19.1 degrees. Cool. Well, that's pretty simple. Now, if you take a look at what you just did, and remember the equations that we looked at earlier, you know that the equation is for your principal stresses is sigma x plus sigma y divided by 2 plus and minus, I guess, the square root of sigma x minus sigma y over 2 squared plus the shear squared. Well, that's really just what you did, because that first part is the center point, sigma x plus sigma y over 2. And then the second point, the square root plus or minus the square root, that's your radius. And so that is where those equations come from. And then for the shear equation, it's just the radius. And so, yeah, it's pretty cool. You can find so much information just from the circle to find out what all your stresses are at that point in your piece. So yeah, that's a basic overlook at Mohrs Circle. There's a lot you can do with it. Just play around with it and you can find out all sorts of things about your stresses and your stress elements. And yeah, it's pretty cool.